We're now about to end this series of video lectures. This is the second last video lecture of the series that is about the Lebesgue integral and its properties. So it's good to give us some perspective. We defined the integral for non-negative extended Borel functions through a set of axioms. Then we use this to define the Lebesgue measure, the Lebesgue integral of general extended Borel functions with not necessarily non-negative by separating the positive part and the negative part. And then we proved almost all of those properties. We could have proved all of them, but we found it more convenient to leave some of them for a later time, and this time is about to come, not now. And now we're constructing it, and these axioms, they included some very convenient and fundamental property, which basically is the property that differentiates the Lebesgue integral from the Riemann integral, which is it is sigma additive. But then using sigma additivity, we found some very simple and dull proof of monotone convergence theorem. And of course, using monotone convergence theorem, we can prove that the measure is sigma additive. What is difficult is to prove one of them. And we just proved the monotone convergence theorem in the previous video lecture. And it is extremely convenient to have the monotone convergence theorem. And why that? Because we have already defined the integral for simple random functions, for simple functions. And we use the definition of the integral for simple random functions to define the integral of non-negative functions. We showed that this definition is monotone. We have already showed that this definition is monotone and that it satisfies the monotone convergence theorem, that it has monotone convergence in the sense that if Fn increases, f is the limit, they're all non-negative, then the integral of Fn converges to the integral of f. And this is extremely useful. And how is it so useful? It is for simple functions. We have already proved that it's linear, that it's unitary. Well, unitary, it follows immediately from the definition, and monotone. So let's focus on the linear part for now. We have already proved it's linear. So we can use the fact that the integral of simple functions is a linear operator and push it to non-negative functions using the monotone convergence theorem. How can we do that? Well, we just need, if we have two functions f, and g, and we want to understand what's the integral of f and g, well, we can approximate them by simple functions and approximate this one also by simple functions and use the fact that the integral is linear for simple random functions to conclude from there that it's also linear for non-negative functions. So this is the jump here that we make. It is, we use monotone convergence theorem to make properties that hold for simple functions to make them hold for non-negative functions in general. So this will be a constant trick that we'll see, and the next video lecture we'll see this trick applied many, many times. On this video lecture, what we're going to show is something much simpler. We're just going to show that it is possible to find such approximation. That if we have a non-negative extended Borel function, we can find a sequence of simple functions that converge to f, that are non-decreasing and converge to f. So in this video lecture, our modest goal is just to show existence of such a function. And then in the next video lecture, there comes the glory. That's when we use existence of this sequence to bootstrap all properties that we are able to establish for simple functions, bootstrap them to non-negative functions. So here's a sequence of functions that I call approximation of the identity. In the next slide, you see why I call it approximation of the identity. So let's look at the formula. I'm considering a specific sequence. It didn't need to be this one, but this one is a very popular one. You see this in many textbooks. It is the following. It takes values at most n, because we are getting a number j, which is at most 2k times n, but after that we are multiplying it by 2 to the minus n. Excuse me, this should be 2 to the n here and 2 to the n here. So we're taking a j, which is at most 2 to the n times n. When we multiply by 2 to the minus n, they cancel. So this function takes values at most n, at least 0, and it takes finitely many values. Okay, this is what this function does. And what it does is it takes the value 2 to the minus n. It takes value 2 to the minus n times of j, this j being the highest, so that 2 to the minus n times j itself is at most x. So because 2 to the minus nj is at most x, when we multiply it by 2 to the minus n, we get something which is less than x. So gn of x, you can see from this expression, is at most x. And let's move forward and see the graph of this function. And that's why it is called an approximation of the identity. The identity function would be this one. That's the identity. That is y equal x. And this function is an approximation of the identity in the sense that it converges to the identity, but it's a very good approximation of the identity. It is an approximation that is a simple function. It takes finitely many values. That number of values it takes increases. It increases very quickly, but it's always finite. So let us exercise here a bit our understanding of these functions. G2, that's when the index n equal 2, it takes value at most. The largest value it can take is 2. And moreover, each integer interval, the interval between each pair of integers, is split into a number 2 to the power 2. But these are different 2's. Okay? This one is the same as this one, which is the same as this one, and this one is always 2. So 2 to the power 2 means 4 intervals. 1, 2, 3, 4. So there are 4 intervals here. This one, this one, this one, this one. And each interval is split into 4 intervals. So this one and this one. So you see this function takes at most 1, 2, 3, 4, 5, 6, 7, 8, 9 intervals. 9, which means n times 2 to the n plus 1. 1 plus 1 because it starts at 0. So this function takes n times 2 to the n plus 1 values. And the same will be the case if we take n equal 1. If we take n equal 1, this function takes value at most 1. And each integer interval, well, there's only one integer interval here, it's split into 2 to the 1, 2 to the 1, just like before here. So the function would be this one. The function would be this one. This would be G1. So I'm not showing the graph of G1, I'm showing the graph of G2. What is important to remark is the following. For each k, gk takes finitely many values. For every x, as we increase k, the value converges. Gk of x converges to x, and it is in this sense that it approximates the identity. It's approximating the function that assigns x to the variable x as k tends to infinity. And it's illustrated here. If we take, again, this will be g1. So if this is my number x, this will be g1 of x. This will be g2 of x here, and this will be g3 of x. So you see how it is approximating x, because x itself is here. So it approximates every number just simply by slicing this interval here finer and finer at each step. And in case it is not entirely clear, G3, G2 of x, G2, it takes values here and here and here and here, but between these two, it doesn't take any value between these two. And since my variable, my point here, x, is between these two, it will take the lowest of the two. That's why it is increasing and approximating from below.